in one go. Let's understand the working principles of the atomic bomb and the hydrogen bomb. First, let's look at the atomic bomb. As those who have built an atomic bomb know, the principle of the atomic bomb is not actually complex. Why is it that this concept, which appears in middle school textbooks, can still only be manufactured by a few countries? The main material for making an atomic bomb is uranium. The atomic number of uranium is 92. It mainly exists in nature as U-235 and U-238 exists in nature. Among them, U-235 contains 92 protons and 143 neutrons, while U-238 contains 92 protons and 146 neutrons. This kind of element with the same number of protons, but different numbers of neutrons is also called an isotope. Compared to U-238, U-235 is very physically active, so it is a more suitable raw material for making nuclear bombs. However, in nature, 99.2% of uranium exists in the form of U-238. U-235 only accounts for 0.7%. If U-235 is enriched to about 4%, it is low-enriched uranium. Enriched to about 90%, it is highly enriched uranium. Low-enriched uranium is used for building nuclear power plants, while highly enriched uranium is used to make nuclear weapons. There's a question. This highly enriched uranium looks unremarkable. So why can it unleash world-destroying power? This brings us to nuclear fission. When a neutron bombards a uranium atom, the uranium atom will split into two smaller nuclei, and at the same time, it will release 2 to 3 neutrons. Scientists discovered through calculations that during the fission process, the atom's mass actually decreases. Where did the reduced mass go? According to Einstein's mass-energy equivalence equation, mass can be converted into energy, and energy can also be converted into mass. Therefore, the lost mass was ultimately converted into energy. The new neutrons produced by fission will then collide with other uranium atoms, continuing to cause fission reactions, thus forming a fission chain reaction. This fission chain reaction will continue, ultimately unleashing world-destroying energy. There are two main designs for atomic bombs. One is the gun-type design represented by the Little Boy atomic bomb. The other is the Fat Man atomic bomb, which uses an implosion-type design. Let's first look at Little Boy's gun-type design. If we take it apart, we will find several rings installed at the front and back. These rings are made of highly enriched uranium. The uranium rings in the warhead weigh about 25.4 kilos. The uranium rings in the tail weigh 38.5 kil. At the tail of the atomic bomb, there is an electric detonator. It is the bomb's ignition device. The detonator is connected to the adjacent smokeless powder. Next is the steel casing, mainly used to enclose the nuclear fuel and detonation device. This upper part is the air pressure sensor port, used to connect to the barometric device. In the middle, there's a long gun barrel. The uranium rings mentioned earlier are installed inside this gun barrel. This is a sensor. Upon receiving a signal, it can trigger the ignition device. These are safety plugs. They prevent the atomic bomb from exploding during transport. This is the tungsten carbide sleeve. It's mainly used to control the critical state of the nuclear reaction. This in the front is the tungsten carbide plug. It has some neutron initiators installed on it. They ensure the chain reaction starts properly. This device is the radar altimeter. It can accurately measure the detonation altitude. Atomic bombs are generally dropped by aircraft before the bomb is dropped. The safety plugs on it are removed 15 seconds after the bomb is dropped. The air pressure sensor is activated to determine the bomb's approximate altitude. When it descends to the predetermined altitude, the radar altimeter on the casing is activated. When the radar altimeter detects the bomb is only 580 meters from the ground, the electric detonator is activated. It will ignite the adjacent smokeless powder. The thrust generated by the explosive will fire the tail's uranium rings forward at a speed of 300 meters per second, causing them to strike the warhead's uranium rings. The massive impact will also cause the neutron initiator to activate. The neutron initiator will release a large number of neutrons. These neutrons will immediately bombard the U-235 atoms. As mentioned earlier, when a neutron strikes a U-235 nucleus, it will quickly fission into 2 smaller nuclei and release energy in the form of heat, while also releasing 2 to 3 neutrons. And these 2 or 3 neutrons will then collide with other nuclei, causing new fissions. This chain reaction will continue. When a certain critical mass is reached, it will produce enormous energy. Finally, the mushroom cloud is formed. The Fat Man atomic bomb has a different structure from Little Boy. It uses an implosion-type design. Now let's take a look at its detailed working principle. The Fat Man atomic bomb primarily uses plutonium-239 Pu-239 as the fissile material. Just like U-235, if you bombard Pu-239 with a neutron, it will also split into 2 smaller atoms, and it will also release 3 neutrons and enormous energy. These neutrons will then react with other Pu-239 atoms, ultimately forming a fission chain reaction. However, a sphere made of Pu-239 is in a subcritical state. If we want the plutonium sphere to undergo a fission chain reaction and release enormous energy, the plutonium sphere must reach a critical state. The method is to compress the plutonium sphere under normal conditions. The space between atoms is large. The neutrons released by fission lose their energy before they have a chance to react with other atoms. Therefore, the chain reaction cannot be sustained. But if we compress it, the gaps between the atoms will be greatly reduced. At this point, the chain reaction can be sustained. The problem is that compressing the plutonium sphere is extremely difficult. At least 300,000 standard atmospheres of pressure must be applied from the outside, which is equivalent to the pressure exerted by 500,000 elephants. Not only that, the applied pressure must also be symmetrical. In order to compress the sphere uniformly, obviously, we can't find that many elephants. But we can replace the elephants with explosives. When the explosives are detonated simultaneously, the pressure from the explosion will press onto the plutonium sphere, but the plutonium sphere gets compressed into this asymmetrical shape. To make the plutonium sphere compress symmetrically, we can place a ring of symmetrical explosives around the sphere. Each part of the explosive is a combination of fast explosive, slow explosive, and fast explosive. This way, when the explosives detonate, the shock wave will converge inward, forming a relatively uniform pressure, which in turn compresses the plutonium sphere to the extreme. At this time, we can place some radioactive element called polonium-210, PO210, near the plutonium sphere. Po210 can release alpha radiation. This radiation, in turn, will be absorbed by the nearby beryllium-B element, which will then release many neutrons. If these neutrons are directed at the plutonium sphere, a fission chain reaction will occur inside it, releasing enormous energy. With this theoretical knowledge, let's now learn about the structure of the Fat Man atomic bomb. The Fat Man atomic bomb is 3.3 meters long, 1.5 meters in diameter, and weighs about 4.6 tons. If you take Fat Man apart, you will find its interior is a layer-by-layer design, which is very complex. The innermost sphere, only 2 centimeters in size, is called the neutron initiator. The inner and outer layers of the neutron initiator are both beryllium. Between the two beryllium layers is polonium. We mentioned earlier that polonium releases alpha radiation, which causes the beryllium element to release neutrons. Therefore, the main function of the neutron initiator is to emit neutrons. Outside the neutron initiator, it is wrapped by a 6.19 kilogram plutonium sphere, only 9.2 centimeter in diameter. The plutonium sphere is then wrapped in a core sphere made of U-238. Its main function is to act as a neutron reflector, reflecting escaping neutrons back into the plutonium sphere, thus increasing fission efficiency. Then the U-238 sphere is wrapped in a plastic shell made of boron. It can absorb stray neutrons, preventing premature detonation. All these spheres are then encased in a thick layer of aluminum. It can transmit the shock wave generated by the explosives uniformly to the central plutonium sphere. Next, the aluminum sphere is surrounded by 32 blocks of fast explosives. They are composed of 60% RDX and 40% TNT. Outside the fast explosives is another layer of explosives. This layer is composed of fast and slow explosives. These explosives are also known as explosive lenses. To detonate these explosives, a detonator is installed on each block of explosive. After that, the entire sphere is encased in a thick steel shell, which is secured with bolts on the outside. This next to it is the X unit. It contains capacitors and other electronic components, responsible for generating a large current under high voltage, and simultaneously transmitting this current through wires to all 32 detonators on the explosives. Over here are the sensors, timers, and radar controllers. On the other side is the battery that powers the X unit and all the sensors. All of these components are enclosed in a large outer shell. A radar altimeter is installed on the outer shell, used to measure the height from the ground. There is also a stabilizer at the tail of the outer shell, which keeps the bomb relatively stable as it falls. After the Fat Man atomic bomb was built, on August 9, 1945, it was loaded onto an airplane. The bombing target was set for Kokura City, Japan. But the weather in Kokura City that day was very bad. With heavy cloud cover, the pilot could not get a clear view. So the plane flew to the backup target, which was Nagasaki. Fortunately, the weather in Nagasaki was very good. A good day for dropping a nuclear bomb. So under the pilot's operation, Fat Man eagerly jumped out of the bomb bay when the radar altimeter detected that Fat Man was only 500 meters from the ground. The ignition system would activate. The X unit on the side of the bomb would discharge, sending a current of up to 5,000 volts to each detonator. In an instant, all the explosives would detonate simultaneously. The resulting pressure wave, exceeding 300,000 standard atmospheres, would pass through the aluminum sphere, plastic shell, and uranium sphere, finally reaching the plutonium sphere. This would cause the plutonium sphere to reach a supercritical state. At the same time, this immense pressure would also cause the neutron initiator at the center of the plutonium sphere to rupture. The rupture would cause the polonium and beryllium inside the initiator to mix. The beryllium would absorb the alpha rays emitted by the polonium, causing the beryllium to release a large number of free neutrons. These neutrons would then react with the plutonium atoms, causing them to fission into 2 smaller atoms and release 2 to 3 neutrons. These 2 to 3 neutrons would then continue to strike other plutonium atoms. Just like Little Boy, the chain reaction would continue to cycle, ultimately producing enormous energy. A giant mushroom cloud was formed, and Japan became the only country in the world to experience atomic bombs twice in a row. Actually, compared to the atomic bomb, there is a nuclear bomb even more powerful, the hydrogen bomb. Next, let's take a look at how the hydrogen bomb is made. The hydrogen bomb is a fusion bomb. It uses the nuclear fusion of hydrogen to produce energy. Hydrogen has only one proton and one electron. It also has two isotopes. One is deuterium with one proton and one neutron. The other is tritium with one proton and two neutrons. If deuterium and tritium are fused together, they will become helium, releasing one neutron and enormous energy. This is nuclear fusion. But there are two problems here. First, how do we get deuterium and tritium? Second, how do we get deuterium and tritium to fuse? Deuterium is easy to obtain. Seawater contains a large amount of deuterium. Through distillation or centrifugation, we can obtain deuterium. But compared to deuterium, tritium is very difficult to obtain. Its quantity in nature is very small. Scientists discovered that by bombarding lithium deuteride with neutrons at high temperatures, one can obtain deuterium and tritium. Lithium deuteride is a stable white powder formed by combining lithium and deuterium. Therefore, it is a suitable nuclear fuel for a hydrogen bomb. Now that we have deuterium and tritium, how do they fuse to release energy? Getting the nuclei of two atoms to fuse is actually very difficult. This is because atomic nuclei have a strong repulsive force between them. But if we increase the temperature to several million degrees Celsius, the atoms will accelerate. However, to make the atomic nuclei fuse, the temperature must be raised to about 100 million degrees Celsius. The temperature at the center of the sun is only 20 million degrees Celsius. The immense temperature can greatly increase the speed of the atoms. This will cause the electrons orbiting the nucleus to break away from it, allowing the nuclei to approach each other. When the distance between them reaches 1 redendus 1552 meters, fusion between the atoms occurs. But how can we achieve such a high temperature? Very simple. An atomic bomb explosion can generate this temperature. Therefore, an atomic bomb is usually used as the detonation device for a hydrogen bomb. Now we know the operating principle of a hydrogen bomb, so how is it made? Let's take the largest hydrogen bomb in human history, the Tsar Bomba, as an example. The Tsar Bomba is 8 meters long, 2.6 meters in diameter, and weighs 27 tons. Let's open up the hydrogen bomb to see its internal structure. The front half of the nuclear bomb is a sphere, which is actually a Fat Man type atomic bomb. We've already discussed its principle. The rear half of the bomb is the hydrogen bomb part, mainly composed of 3 parts. The outermost layer is a cylinder made of uranium. Next is the white nuclear fusion material, lithium deuteride. The innermost part is a plutonium rod. Then the entire interior of the hydrogen bomb is filled with polystyrene foam, like the atomic bomb. The hydrogen bomb is also dropped by an airplane. When dropped, the entire aircraft was painted bright white to reduce the thermal radiation from the hydrogen bomb's explosion. Accompanying the aircraft was an observation plane used to film video footage and collect explosion data. When the Tsar Bomba was dropped, the parachute at its tail would open, thus slowing the bomb's descent to allow the delivery aircraft enough time to safely leave the blast zone. The bomb has a built-in air pressure sensor that measures the altitude from the ground. When it is 4 kilometers from the ground, the atomic bomb inside the hydrogen bomb will ignite first. The sensors inside the atomic bomb will send a signal to make the detonators release an electric spark. This will cause the shaped charges inside the atomic bomb to be rapidly detonated. The explosion will produce a large amount of high energy, gamma rays and X-rays. The rays will cause the polystyrene foam inside the hydrogen bomb to turn into plasma. The high heat and pressure from the plasma compress the plutonium rod. Compressed past the critical point, the lithium deuteride begins to react, producing tritium. Then the atoms inside the deuterium and tritium will, under the 100 million degree high temperature from the nuclear fission, undergo intense nuclear fusion. Nuclear fusion produces enormous energy and generates helium. At the same time, it also generates a neutron. The neutron reacts with the outer layer of uranium and the central plutonium rod, which will trigger new nuclear fissions. The new nuclear fissions will then cause the lithium deuteride to produce more nuclear fusion. Fission and fusion interact with each other. Finally, in less than a second, enormous energy is produced. The mushroom cloud can reach a height of 60 kilometers. From 1,000 kilometers away, this mushroom cloud can be seen. Wherever it goes, it brings total destruction, and all things return to nothing. 射线会导致氢弹类的氢弹类泡沫转化为等离子体产生的高热高压挤压不超过临界点，刀化里开始反应产生，接着刀河川内部的原子核裂变产生1度高温下会发生剧烈的核聚变，产生巨大的能量并生成氦，同时还会生成一个中子跟外层的油块和中心的不爆反应，又会引发新的核裂变，刀化里产生更多的核聚变和聚变互相作用，最终在不到1秒的时间内产生巨大的能量，蘑菇云高度能达到60千米。